Okay, there we go. So, okay, so I'm sure everybody knows, but our story begins with the jitterbug. Um, that's Bucky with the jitterbug, and yeah, so I mean, it was inspired by this dance from the 1930s. And from what I understand about the jitterbug, is that within its motion is contained at least four of the Platonic solids. So you have at the full expanded state, it has the cube octahedron, and as it contracts, you see the icosahedron, the octahedron, and when it's completely folded, you see the tetrahedron. Um, and then, of course, because that's just like a wireframe structure, Bucky, and I guess Duncan, Stewart, and Joe then um, put faces on the triangular sides of the jitterbug and made this other single cell jitterbug piece in 1976, which Joe then put two faces on each side, which gave the structure stability. And he also explored face-to-face transformations, face-to-face along an edge transformation. These are all the tetrahedral jitterbugs. And then face-to-face through a vertex transformation. Can you guys see the vertex one, or is everyone else's video coming on the screen? Yes, you can. Okay, cool. So yeah, and then H.V. Hervane then basically described and analyzed the motion of these structures. 1989, the complete set of jitterbug transformers, an analysis of their motion. So I was studying at RISD basically, and there's a lobe collection there in the nature lab, and I got to see a couple of these structures there. And actually, there was nobody at RISD who could kind of point me in the right direction. Well, there was the design science symposium, but I did not join that at that point in time. But yeah, so the first time I'd actually seen any written literature on the di-polygonoids specifically was was this paper, I guess, and I guess through googling Bucky's work. Okay, so I'm just going to start with the equilateral triangle and its threefold symmetry. So of course, if you rotate, from what I understand, again, if you rotate an equilateral triangle 3 times, it translates at basically 3 times in 360 degrees, and that's what it means by an equilateral triangle having threefold symmetry. And interestingly, of course, a threefold tessellation made of equilateral triangles also, when rotated 3 times around at 120 degrees, translates. So therefore, it also has a threefold symmetry. And here we have a tetrahedron, equilateral triangle with a threefold tessellation on it. And that is a self-similar module, basically. So the threefold tessellation on a threefold polygon is a self-similar module of, of just like a threefoldness, I guess. So yeah, just moving on. A Moire pattern. This I'm just going to read out from this because I also don't. It's like an interference pattern that can be produced when an opaque ruled pattern with transparent gaps is overlaid on another similar pattern. And in physics, interference is a phenomenon in which two waves superpose to form a resultant wave of greater, lower, or the same amplitude. So here we have like a graph of like these red waves, and they are basically amplifying each other to create a larger wave, and the other one they cancel out. Okay, so I began experimenting just by like building a couple of these structures, and here we have this Moire cell, which is basically the tetrahedron di-polygonoid expanding, and it has a 120-degree period. So what that means is at 120 degrees, the Moire pattern basically completes a cycle and completes one period of the Moire pattern, and 240 degrees is where the structure basically expands and then contracts. So that's 240 degrees. 120 degrees is the expansion and 120 degrees is the contraction. And again, when I'm talking about degrees here, it's literally like in 2 dimensions. I'm talking about the triangles rotating 120 degrees. I'm not sure about how to explain the motion in 3 dimensions. So yeah, the only thing in 3 dimensions I know is like a dihedral angle, I guess. But yeah, so that is that. And if we kind of analyze the motion, what's happening there, is at 0 degrees, the grids are completely overlapped, so you don't see any Moire pattern. And it basically magnifies in. At about 30 degrees, you see this intricate dance. And at 60 degrees, the grids overlap. But interestingly, at about 58 degrees, this pattern, the Moire pattern of equilateral triangles that is also there. So I mean, yeah, so sorry, let me just step back a bit. So of course, the structure itself is made of equilateral triangles, which is the tetrahedron. The grid is made of equilateral triangles, a self-similar module. And the animation is also equilateral triangles. And at about 58 degrees, we see the equilateral triangle pointing upwards. So the question is basically, why is it not a 60-degree period, and why is it a 120-degree period in the animation? And the answer is, of course, because when after 60 degrees, the grids overlap, when it's magnifying again, the equilateral triangle is pointing downwards. So that's how one kind of knows that it takes a 120-degree cycle for the Moire pattern to complete, basically, the one period. Is, yeah, I guess because the equilateral triangle is pointing downwards. So the pattern basically inverts after about 60 degrees. So that, to me, I guess, is like the simplest threefold pattern. I mean, it's not, I guess a tetrahedron is the simplest threefold pattern, but in terms of Moire, I guess this is, in terms of interference patterns, it would be a very simple pattern just made of equilateral triangles. Yeah. So, and here's a physical version that I had made. Yeah. So, I mean, of course, Joe keeps pointing out to me that in the mathematical realm, the tetrahedron can kind of invert, the structure itself can invert, and I'll show you an animation of that as well. But in the physical, and that's true for the octahedron and the other symmetries as well. But interestingly, the tetrahedron in reality, like in a physical structure, I mean, unless you have magnets over here as a connection system, in which case they can kind of, like in terms of the connection system, if you had magnets, maybe it could continue instead of getting stuck like at this point. Also right now, because it's a physical structure, it doesn't completely overlap because of the connection system. So, and in the acrylic sheets on which this is made, so this is made on this is made on acrylic sheets and graphic stickers basically. So I've just printed out stickers and stuck them on acrylic sheets, rivets at the center, and small stainless steel rings basically. So I guess, yeah, one doesn't see it completely overlap over here, but that would be the physical version. And the digital version and the physical version work the same for the tetrahedron. It's not necessarily the same for the octahedron because, or the icosahedron, because those also only expand up to 120 degrees. But here's the chiral 720 degree rotation, which Joe has, I guess, discovered and worked on. And this is an animation made by Adrian Rossiter in the UK. And interestingly, over here, the way Adrian has visualized this is basically starting from the expanded octahedron position. So of course, when the tetrahedron expands, it's expanding with 4 equilateral triangle gaps. So that you see right here, there are 4 gaps which are also equilateral triangles. And this structure is going through a 720 degree rotation. And so basically, if one had to put the Moire pattern onto this, which I am sadly not good enough at computer graphics to make that myself yet, but yeah, that would have 3 Moire periods within it because it's a 720 degree rotation, and I guess 1 Moire period. Actually, no, that would be 6 of them, right? I guess 120 into 6 is 720. Am I right? Yeah, yeah. Okay, anyway, so, and here I just did like a couple of other visuals of the tetrahedron. So here I've basically just put dots on each face and just to trace the trajectory of the motion through that 120 degree, 240 degree expansion and contraction. So this would be the trajectory visuals, I guess, which Joe has also done a different kind of version of, but he's, I guess, done it with, and even Duncan Stewart has, of course, with, I guess, just along the vertices of the chiral expansion. But yeah, I'm just going to play that again once more. Okay, so what happens when one uses checkered threefold grids? Now here we have two checkered grids, the opposite of each other. You can see, I guess,
Yeah,
on the
hi,
left,
Carl.
the equilateral triangles are the white equilateral triangles are pointing upwards, and on the right structure, it's the opposite. So I guess here's an animation of two, first of all, two identical.
Yeah, I had the,
Going through 360-degree rotation.
yeah, it's on now, and I had trouble getting in too.
Hey, Don. By the way, I forgot to say right at the beginning that I'm extremely honored to be presenting today. Like to thank Don and Joe and Sam and everybody else who's here attending as well. Carlo, thanks for coming as well. Yeah, I forgot to say that. Honored to be presenting to you guys this work. Um, so here is the pattern of identical checkered grids, basically. I'm just gonna play that again. Um, so yeah, the question is, what happens when one uses identical checkered grids instead of just a wireframe equilateral triangle tessellation? And this is what one sees basically. Um, yeah. So, and here's of course the physical version of the octahedron. I call it the Moire Cell. And this one, the grids are basically the two alternate checkered grids. So when the structures completely overlap, one sees just black because I guess the black triangles are overlapping each other. Um, so that is the octahedron cell with alternate checkered grids. And yeah, so yeah, of course, what's super interesting about that is a square interference emerges rather than a triangular interference. And coincidentally, the octahedron, when it expands with 6 square gaps. I guess you can see that here again one more time. But so yeah, of course, the tetrahedron expands with 4 triangular gaps, which is why I thought it was appropriate to have a wireframe Moire animation of triangles. And because the octahedron expands with 6 square gaps, it made sense to have alternate checkered grids. Because here you can see the expanded octahedron state in the physical model has 6 square gaps. And of course, the chiral expansion of the octahedron is a 720-degree expansion. So, but the period for the Moire is 360 degrees. So it would make sense because the physical structure only expands 120 degrees to use the chiral expansion for the animation. And here again, the animation starts at the cuboctahedron phase of the structure. But if one started the chiral expansion with the octahedron, then that Moire would make sense. So basically, it does matter where one begins the chiral transformation from. If one starts at the octahedron phase, or here, for example, this would be the beginning, which is the cuboctahedron phase of the chiral expansion. So that matters for the Moire period basically, and for whether the structural period and the structural cycle and the Moire period match up. It does matter. And here is just a dynamic view rotation, which I guess Kirby really liked, which I think he had seen on YouTube, of a 120-degree period with a wireframe, as well as the trajectory of the octahedron with the faces. I will play it just once again. So yeah, there, and it's very tough to see also. This is like a really well rendered animation, but it's very tough to see the actual Moire pattern through these kind of visuals, because I mean a lot of photographers, for example, really hate Moire because it really interferes with their photographs, especially of clothes and things like that. And of course, with the icosahedron, I've used just because I'm not sure exactly which moire to use for the icosahedron, because when it expands with pentagonal gaps. But here is the icosahedron expanding with wireframe equilateral triangles, and it is this would mimic the physical structure with a 120-degree period and a 240-degree cycle. And of course, the chiral transformation. Again, starting from the icosahedron. That's because the icosahedron di-polygonoid expands. You can see right there with pentagonal gaps. So again, I'm not sure what moire pattern would be appropriate for this, because yeah, I mean, of course, triangular ones would be the most appropriate, because I mean the icosahedron is made of equilateral triangles. But yeah, I just used wireframe ones, I guess, for this one. And sorry, I just stopped that midway through. But here is the trajectory of the icosahedron, the vertex view, and then the face view, and then yeah, it's just like on each face, I've just put a set of dot patterns to see where each dot kind of yeah, moves, and a dynamic view. Yeah. This is also the issue, is like my limits in my ability to animate these things. Okay, anyway, moving on to the square and its fourfold symmetry. So of course, if you rotate a square through 360 degrees, you get 4 instances of symmetry. So the square translates 4 times, and therefore the fourfold polygon has fourfold symmetry. And that is true for the fourfold tessellation as well. And here we have a self-similar module, wireframe module of the fourfold gone, I guess. And to see the interference of that, it also, of course, the moire period of squares is also 90 degrees in the square tessellation. And what happens when one uses alternate checkered? Oh, by the way, I have a physical structure of that, but I guess I'll show that after the presentation. But here we have alternate checkered fourfold grids. So when one overlaps both of these, it's just completely black and opaque, because so here we have the moire box with a 180-degree period and cycle. And again, this would be, I guess, a very simple, and I guess this structure, as well as the octahedron, as well as the tetrahedron, would translate, I guess, into all higher dimensions as well. Yeah, so here we have the cube dipolygonoid composed of 6 squares, and it's played one last time. And it's, I guess, a regular 3-dimensional pattern, because the structure, grid, and interference are all made of squares. And here's the physical version of that as well. Again, the structure is made of acrylic sheets, and they're just like 1 mm thick acrylic sheets, and graphic stickers basically that I've stuck onto the, so it's not exact. And again, here you don't see the full, you don't see it fully opaque, because the acrylic sheets don't fully overlap because of the connection system. But yeah, it would be cool to like have a gigantic installation of this and be standing inside it, because one cannot really ever see the full box, because you can only, I guess, see one side of it, or I guess bits of 2 sides. And anyway, so here is the chiral 720-degree rotation of, again, starting from the cube octahedron phase of the cube dipolygonoid. Yeah. Okay. So, and I'll just play all 3 of these together. This is, I think the face view one looks really cool. It's just like a frame, quite cool, and looks very floral when the expansion happens. And that's just like a perspective view of the trajectory of the, yeah. So the pentagon in its 5-fold symmetry, again, you rotate a pentagon 5 times to 360 degrees. Now it's interesting with, of course, we all know that pentagons don't translate into tiles in 3 dimensions, but there are quasi-crystals. So what patterns, of course, are appropriate for a pentagonal or a dodecahedral di-polygonoid, and I guess quasi-crystals and Penrose styling works well or is appropriate for that because they also obey 5-fold, 10-fold, and 12-fold symmetries. And from what I understand, in 5 dimensions, you can have perfect periodic quasi crystal lattices, which then are sliced at phi into 3 dimensions and then projected to create these 2-dimensional dot patterns. And here we have a self-similar quasi-periodic set of symmetries on a dodecahedral dipolygonoid. And I've created one animation as well with the same thing. Yeah, I mean, yeah, I guess I will slowly rotate this from the expanded to the contracted state. So you can see one of the animations there. They're quite beautiful, by the way. So the Moire patterns of quasi crystals are, I think, like the dot patterns specifically are quite awesome to like view. Because they have all these like circular symmetries within them. So as the dot patterns rotate, you see all these cool kind of like circles showing up. Here's a dynamic view one. Again, very tough to see the Moire in this, but just kind of showing the symmetry of this dodecahedron dipolygonoid. Should I just play the one of these again? I guess I'll just play both of these together. But yeah, and here, of course, with the, like I think already mentioned, but the dodecahedron expands with 20 equilateral triangle gaps. So again, it's very interesting with all these structures. They expand into their duals, I guess, yeah, except for the octahedron and the cube, which both expand into the cube octahedron. But yeah, this structure in the expanded state is the icosahedral dodecahedron. So it expands with 20 equilateral triangles, and the icosahedron expands with 12 pentagons. So they expand into their duals in that sense. Yeah, here again, we can see at the expanded state there, 20 equilateral triangle gaps. And here is the chiral rotation of the same to 720 degrees. So again, like I'm not sure which specific quasi-crystal pattern to put on any of these structures or which one seems the most appropriate for this, but I guess there are infinite possible quasi-crystal symmetries, I guess. So not sure again which one was the most appropriate as a Moire pattern for the dipolygonoid. Oh, also, by the way, so in this chiral rotation, I'm sure as everyone who knows about this already knows, but the pattern also inverts. So when it's in the fully expanded states, well, so now you see this, the blue face is on top. So the same way the Moire pattern inverted in that tetrahedron structure, even the tetrahedron Moire, the structure also inverts in this case in the chiral rotation. So here now again we see the orange face on top. So yeah, which is why it's not a 360-degree rotation; it's a 720-degree rotation. And here's the trajectory of the dodecahedron dipolygonoid. So just a bit on like how I started this. Of course, in college I had seen some of these structures, and the first thing I had made was I was really kind of in love with optical illusions also at that point. So I had made this like phi spiral optical illusion, thinking about just looking at the interconnectivity of the structure and how you could kind of open and close the structure from any different point on it. So I had just made this optical illusion one, and then I realized, oh my god, you can actually just put any pattern on this. So then the issue became what patterns to put on each structure and what seemed the most appropriate. So therefore, like on triangles and tetrahedrons, it's obvious to put equilateral triangles. So this one's just a universe box. So there we have like, I mean, I guess a universe octahedron would be more appropriate, but that's a carbon atom. Here's a quasi-crystal molecule. There you can see those beautiful like circular rotation symmetries. Then I had put like the lunar cycle and the solar cycle. Yeah, again, that's not exactly how each of these motions work, but it was just like a fun idea to put this on a box. The planets moving around the sun. And again, just to show how they're all interconnected with these different scales of reality. A black hole in the center of most spiral galaxies with this pi-spiral optical illusion. Um, and the universe expanding and contracting with the square Moire pattern. And I guess if you had put quantum and like life at the biological level with evolution, one would have an octahedral symmetry rather than like a square symmetry. And this was like my first notebook where I just kind of like realized these ideas. Um, and yeah, some of the early like how I had started the process. I mean, we don't have 4 moons, but I just was not able to show all the whole cycle of the moon, so I just put 4, I guess, holes over there. And this is, I guess, inspired by like zoetropes and early animation techniques. So I was thinking about those as well um, when I was thinking about how one could create stuff on these boxes, animations. So there are many ways, I guess, also of animating kinetic structures that expand and contract and have different kinds of motions. Another early experiment with the aluminum sheets was by just cutting off the vertices, you kind of limit the expansion a bit more. So it's not a full, in this case, it will not be a full 90-degree expansion. And that's because of the connection system. Of course, the golden ratio sunflower phyllotaxy. And here, of course, it does look, the Moire pattern does look a lot like if you just stare at the sun directly. And that's, I guess, also because the sun follows the same principles of kinetic energy expanding outwards. So this is just like a, yeah, like a golden ratio Moire trippy pattern, I suppose. But it also does look, I guess, like the sun, which is interesting. And yeah, I guess everyone knows, but here each dot is about 137 degrees away from the next one, which creates this beautiful golden ratio dot pattern. And then I was trying some different structures. This is a pentagonal antiprism. I really want to put triangles on this one as a graphic screen, so it would just be like a triangular moire. But yeah, just playing around with a few of these structures and symmetries. Yeah, just let that play, I guess. This one is 10 tetrahedrons. Radially expanding as opposed to some of the other expansions that we've seen so far, which are just, yeah, I guess Platonic expansions. And I guess, again, because geometry is infinite as well, and so uniform polyhedra, there's so many of them, one can try using any structure with equilateral triangles, squares, and pentagons, and hexagons and stuff as well. Even though they won't be regular or Archimedean for that matter, you can still make cool structures. I don't know if you can hear me, but I'm going to switch off my audio. I'm going to switch off my audio for this one. Because there's bad music playing in the background. Sorry. Yeah, so there we just had, I guess, the same sunflower pattern and a few other cool symmetries. And the middle one is cutouts, which also make some cool patterns. And color, of course, color. So yeah, so I guess that's the end of that. Possibilities, we all know magic angle graphene physics is this new thing, so I guess 3D graphene structures could be a possibility. But again, this is way out of my depth. Architecturally breathable buildings, and I guess all these things have been explored without the graphic aspect of it, but graphene based structures and all these new kind of rotational uh, molecules, chemical things, which one can do stuff with 3D geometries with. One can use these same di-polygonoids and 3D geometries that are kinetic and expand and contract to create some cool stuff, I guess, technologies, and research into high dimensional Moire patterns as well, because now that we know that, I mean, you see that tetrahedron Moire Cell, for example, would be a regular three-dimensional animation because the structure and the two-dimensional Moire both have the same period and cycle. One can, I guess, reason upwards through higher dimensions. And of course, I mean, I have to, I guess, also motorize some of these things and create some nice lighting and art installations. And then I was just thinking, again, way out of my depth, but because these are di-polygonoids and each face has two layers, one can think of like the inner layer as like a real plane and the outside layer as a complex plane, and just see what kind of graphs and different patterns one can come out of that. I was thinking of just slapping on the Riemann there's like a video by 3 Blue 1 Brown on YouTube showing this really good visualization of the Riemann hypothesis with this critical line on the half line of the x and y and the complex plane. So what if one can just, for example, put that onto the event horizon of a black hole and use Lorentz attractors? These are, again, just concepts I understand conceptually, but not the actual math or anything like that. So I don't know if it's actually possible. But you could then create loops if you using these dipolygonoid structures if you use the real plane and complex plane together. Oh yeah, I forgot to play this video. But yeah, so I just basically put the graphs that I saw on that video onto this, and yeah, x-axis, y-axis, and yeah, and it's just going to expand the same way. Yeah, but if you allow full 360 chiral expansion, then you could see these dots on the critical line creating loops, and then if you keep expanding. So the thing is, with the square, with the cube, for example, if you cover the gaps, you can expand the next structure. If you cover the gaps of the cube octahedron, that structure will expand further and further and further. So all these structures are interrelated. Anyways, so yeah, that was the end of my presentation. Thanks, guys. Yeah,
All right. Nicely done.
Thank you.
Yeah.
Yeah, that was awesome.
Thanks, guys. Yeah, don't know what to say. Yeah.
I couldn't help but start visualizing these same patterns on a spherical surface. I just wonder if you ever explored those interference patterns.
I was thinking of, you can just take two bowls, like transparent bowls, and put, I'm not sure what circular pattern would work on that. You could just put circles along a latitude or a longitude, or you could put just create a lot of latitudes or a lot of longitudes and create that kind of, I guess, what were you visualizing? Yeah.
Well, even just an arrangement of circles on a sphere, like kind of spherical tiling of any sort on a spherical surface. I could probably share something with you later, but I have an apparatus I designed earlier where it's a arrangement of concentric spheres that kind of rotate within each other using magnets, so it has complete freedom of rotation. I implemented with only kind of a spherical ring, but it could be expanded to a spherical shell.
That reminds me of Flower for Life. The flowers of Symmetry. Yeah. Sorry, go ahead. Yeah.
When most of your visuals right now are done by the models themselves, and you're just beginning to get into animation, right? And so that's one reason why you're not taking it the full 360-degree cycle. Because when you do that, there's a potential, I think, and Carlo, you might find this interesting, that you can take the fourth dimensional illustrations that are very commonly used to show the fourth dimension for, let's say, the hexahedron or the cube. And if you start that out with the planes passing through each other, through the center, So in the fourth dimension, you'd have the 8 cubes passing through the center. And then expand that outward. What will happen is you'll end up with an array of cubes. So if you have the 8 cubes that are very commonly illustrated for the fourth dimensional geometry of the hexahedron, then do the expansion, you can end up with an array of, actually it'll be cubes, it'll be the cube octahedron and the octahedron close packing. And I'm wondering if you did that with moires on the surface, if you would start to get an indication as to what that transformation would be in a very visual way, especially if you did that with stereographic images, left-right images, so that you could see that in the 3D transformation going from the fourth dimensional geometry to a third dimensional geometry. So by doing that, you might be able to start to see some very interesting concepts or things that are happening and going on in that transformation, which brings me back to Don Verdel's work, where Don, you're thinking sometimes of the what do you call it, the matter and antimatter, one being hiding the other.
Yeah.
They're both common, both there at the same time. A moire pattern may start to show you a method or a technique by going through that fourth dimensional to the third dimensional phases. You might be able to begin to see a way that the physicists could determine whether your concept is correct or not.
Very interesting. That's a great idea. I'll make it
during that transformation, you're always going to find some level of being out of phase. So if it's out of phase, you may be able to start to recognize the patterns that show and measure that being out of phase and be able to determine whether you have the matter and antimatter combination always in the cycle. Anyway, it's a thought.
It's a good thought. Excellent. I was thinking of these Moire patterns as a way to look at the plenum, the structure of the plenum, and how arrangements of these units of, well, it's a black and white issue, but as these units move around, that it would indicate certain patterns that could generate from the plenum and condense into matter patterns that matter has. That's what I am really intrigued about Prithvi's presentation. I want to work with that.
This is way out of my depth personally, guys. Yeah, yeah.
So I find these discussions about higher dimensions really fascinating, but I got lost right at the beginning. So please try to help me a little bit more. Are we really thinking about actual three-dimensional little units like tetrahedra and the like, black ones and white ones, and then looking basically for the Boolean union of all the black parts or something like that? Or are we just looking at the coloring of the faces of these higher dimensional objects? I mean, is the moire actually being formed by three-dimensional little geometries that partially overlap? Or are we just still looking at two-dimensional patterns on the surfaces of these four-dimensional objects? I got lost there. Yeah, Prithvi, you probably should.
I mean, like,
that.
yeah, one thing is that I also was not sure whether these are actually three-dimensional moire patterns, in the sense they are still just planes. They're still just two-dimensional planes. It just happens to be that the di-polygonoid structure expands 120 degrees and the moire period is also 120 degrees, but they're still planar moire patterns. But again, if you take like the center of that tetrahedron, for example, and just project the same threefold lattice outwards in every direction, and then still rotate the same di-polygonoid, that would be a true three-dimensional Moire pattern, maybe. So this is just the plane. Or if you take the same plane, and extend those triangular things all the way inwards to the center, and then do the same rotation, that would be a true three-dimensional Moire pattern. And structurally, one could, yeah.
Would picking the pattern that you look at for the Moire possibly come from projecting out of a closest packing sphere that has a number of levels, and then projecting what that interference of the lines of force would be onto that plane of that large packing? Would that give a possible pattern that might have kind of a roots in the structure having that depth, but we're looking at it at a planar level? Is that, I'm not sure if I'm saying that well enough. No.
Well, I think it could be what we're seeing is a projection from a higher dimension, and it's just visually representing higher dimensions.
I have there's a very interesting pattern, okay, that shows up, and this is a full 360-degree pattern of the transformation on a question. Let's see, I forget which one it is, but anyway, and something very interesting occurs. Now, this is a two-dimensional orthographic projection of the paths that the vertices follow during that full 360-degree transformation. If you take that image and look at it by itself, it has a tendency to want to come off the page. So you're getting a three-dimensional effect, and that's coming from the mores of the individual dots that are projected onto there. So in some ways, I'm wondering, when you do that, I mean, I notice your models and you focus a lot on your models as being the two opposite planes and the moire patterns that come out of that. But what's coming out of those that are coming in at an angular relationship to each other? You're getting a whole different effect and a whole different set of mores. So in a way, you're starting to get a three-dimensional volume of that. Now, another way to probably really study that would look at those as in let's say an affine projection, or you look at it in a perspective projection, or rather than an orthographic or a projection. What the differences would be in those transformations and the images that you would get by looking at it in different different projection methods. Because I think that in a sense you're starting to gravitate toward looking at it as a volume, not as two planar elements. And that's what intrigues me. Yeah, sorry.
Oh, that's okay. So that kind of ties in with what I am seeing. And this may be, no, I don't think it's way off at all. I shouldn't apologize before I say it, but it goes back to virus structure from last week and the whole idea of quasi-equivalence theory of Casper and Klug that's applied to our understanding of most viruses as being icosahedral. So you have, the helical and icosahedral and spherical shapes of viruses, but it's actually much more complex than this. And what seems to be happening is what mathematical biologists are starting to explore and find out, and that's Raden Twarak. She is a mathematical biologist at University of York, and she's been looking at the structure of viruses that don't have fivefold symmetry. And what she's been able to do is show a superposition of form on the outside that looks very much like what you're finding. And she connects it to fourfold, not fourfold, it's a combination of different kinds of symmetries, translational symmetry, rotational symmetry. And then when you superpose, or the superposition of those actually is a lot more detailed understanding into the structure of viruses. So they're teaching us something that your Moire patterns are showing, is this nesting quality of various different forms, both fivefold, fourfold, both polygons, polyhedron, polytopes. So this whole thing of moving beyond dimension and using self-similarity on many different levels, Radon's work shows some really exciting, absolutely new perspectives with regard to the form of viruses, and your Moire patterns in a three-dimensional form, jitterbug form, lattices overlapping, and what you're showing is if you do a cubic or if you do a square, depending on what framework you're using, you'll get either a quasi-crystal type pattern, fivefold symmetry, or you would get one that's more representing the fourfold symmetry of the cube octahedron and all the fourfold symmetrical Archimedean polyhedra. So I think what you are doing is showing the same thing that Radon Twarak's work is unraveling and describing in many, many, many papers on virus structure right now. She is the, to me, I think she is the next person in line from Casper and Klug theory to virus structure, or the structure of the sphere that has many different symmetry relations on every level. Nested viral structure, not just one type of structure like icosahedral fivefold symmetrical structures. So she shows how twofold on the surface connects to two-dimensional on the surface, the planes that you can see, the relationships between the capsomers and the and also the envelopes of virus structure. She shows this visually, and it's exactly the same thing that you're doing. So, I mean, her work might be good to describe or explain some of the mathematics. Although, Carlo, I love your work, Carlo, and I think that you would have a much better understanding of the mathematics that is shown as far as nesting or, you know, scale-free, multidimensional form.
I don't know about that, and I have a few remarks later, but I think Prithvi had his hand up to respond to Bonnie, so you go ahead, Prithvi.
I was just going to say the only math thing that I've heard from some friends talking is that one can describe these structures through Fourier transforms and assign an eigenvalue to each of the symmetries, I guess. So, and that's, I don't know what that means again, but I know that apparently that is possible.
Yeah, so I'm still having trouble, going to these higher dimensions. And I think even to really visualize three-dimensional objects, we have some difficulties if you want to present that, in a presentation like that. And so if you just look, say, at cubes and just look at the convex hull of a cube or a dodecahedron, well, yeah, we can kind of infer what's happening on the backside. But you actually get a better understanding of a cube or a dodecahedron if you use sort of wireframe models. And by the time you go to higher dimensions like this tesseract here, a four-dimensional hypercube, I think if you start filling in faces and blocking, part of the information, it's really, really difficult. And that's why whenever I talk to kids about, the 4 dimensions, I always show wireframes. And I think it allows you to kind of see into these objects and to the backside, and you can use perspective projection. So the back cube and the center here, which is kind of yellowish, is smaller than the front cube, and they kind of understand that. So given now the concept of combining different shapes that intersect with one another and forming a Moire pattern, I have the crazy idea, maybe rather than trying to have three-dimensional elements and somehow overlap them, it should go in the other direction. We should go to one-dimensional elements. And so what I'm proposing is, it might be worthwhile to look at higher dimensional regular polyhedra in their wireframe mode, and then have intersecting, overlapping, four-dimensional objects in wireframe mode rotating against one another. And what we're looking at is at the pattern that are being generated by just the wireframes of these objects. It's not exactly a Moire pattern, but it will have sort of some similar effects. And I just wonder what might happen if we go there.
Now, the other observation I have, because I haven't really explored these Moire patterns in any detail, but you are adding motion to the object, and either there's a translational motion that has one effect, but that rotational motion introduces multiple speeds, like the speed at the objects or points further with a larger radius are moving faster than ones with a shorter radius. So you got that combination of motion that is being observed through the Moire pattern. That's an interesting piece that I think ties extra dimensions to what we see, because now it's an angular motion. In fact, I can't help but think of other ways of applying motion. So as opposed to just having a circular clock motion, have like an orbiting motion where the center has some modulation to it. So you add a second level of motion to the overall pattern. And I'd be curious as to what you'd get if you had the angular rotation, but an orbiting center. That could reveal a lot of other things that would be interesting to see.
I had a quick question. I wasn't sure, but when you were doing the original one and you were showing the interference patterns, and there was one point where there was a triangle, it looked to me for a second, and it kind of plays back to what Joe was saying, that I didn't feel like I was looking at a triangular tiling. I felt that I was looking down at the face of an icosahedron, that the angles that were coming back off the ones had a little bit more of a three-dimensional take to them, as if I was looking flat down at the face. So it didn't seem to me to be suddenly a triangular tiling. I'd have to see it again because we were moving through it, but I thought that might be worth kind of looking at what the outside of the triangle, what the angles are there. I don't.
Should I replay that the animation?
Not now for time wise. It was just something that might be worth looking at, I thought.
I also see a lot of similarities in about a month or two ago, Nate gave us a presentation on his harmonoscope, where it was basically taking two sine waves on a plane and mixing them together to give the illusion of a three-dimensional path of particles. I see a lot of similarities in those two different pieces of work.
Yeah.
So we have 4 points, right? You have the interference, some sort of perspective from behind it, and then the observer. And so that's where we're looking at our projection concept. Even though we're doing it with less material, like that's kind of what if we were to make it manifest, I don't know if does that make sense? Like,
well, two different observers from different angles would see different things.
Right. No, that's what I'm saying. It's just like this whole, the event of the interference patterns is you've got interference, you've got something coming through it to cast a pattern, and then you have an observer to see that difference. There's kind of 4 components to it. Or not. I'm just going to slide over here to the side.
There would be another pattern if it was sped up to extreme motions. We might be seeing a whole different pattern emerge rather than the slow development, which is what's happening in reality. Our reality is flashing by at the speed of light. And it's quantized because we live in a quantum universe, but it's flashing by at such a speed that it seems continuous. And if you could slow down reality to pass by at slower speeds, we would start to see different kinds of patterns. The pattern we have now is this speed of light pattern. And as Joe was pointing out, we've got two surfaces, so to speak, that are doing things perceptually based on their movement. And if that movement is sped up, I think we'd see emerging a whole new pattern, which might be quite interesting to, I don't know quite how we do that, but it might be really interesting to see.
I was thinking of the golden ratio dots and on the cube expanding. And if that was sped up really, really fast, would the sun actually mimic kinetic energy expanding outward like that? But,
yeah.
It'd also be interesting to see if there was any color that could be added to this, where you can get overlapping colors to add another layer of modulation to it.
Have you had 3 screens?
Yeah.
Yeah, 3 screens.
Red, white.
Again. Sorry, yeah.
Red, white, and blue.
I was gonna. Yeah. I've made a few RGB versions of those also, but also screens. If you had screens again, if the structure is like, for example, you take the cube, and you have screens going all the way smaller and smaller down to the center point, and then all the way up to infinity. And what would the connection system for something like that look like? It would not be an alternate binary connection system like these. You could maybe connect all like one layer with the next layer connecting with the next layer. Like it would be like a, the connection system would be slightly different, I guess, as well. Should try that out.
Showing up in sequences, not all at once. Is that what you mean?
Well, I think what you're referring is it'd be more like recursive. So each plane would have a reference plane. If that plane moved, then the second plane would move in reference to the first plane, and the third plane would move as reference to the second plane. You need to have that sort of recursive, or I'm not sure the best way to describe that, but you'd have a dependent relationship, like a parenting sort of arrangement.
Physically, yes. Because as you expand the first one, like even with the physical structures, if I expand it from like one side, it takes time for the thing on the opposite side to actually move. I mean, that's just like a energy thing, I guess. I don't know if that's what you meant. But,
like Gary's fields.
Oh, again, I'm pushing for like the simplest experiments first. What I would like to see is just 3 overlapping planes and their Moire effects between them. But we have 3 planes in different colors, R, G, and B, red, green, and blue. And we essentially use the computer graphics combination. So wherever simultaneously you have R, G, and B, you get white. And where you have none of them, you have black. So what would be the kind of Moire patterns that we now get in color as we have these 3 planes of rotating against one another and maybe even translating against one another? Of course, the question is, what is the relative motion if you have 3 triangles, right? 2 triangles, you only can't do much if you keep the centers combined, except there's one angle that defines it. But now with 3 triangles, you already have a question, how do they rotate against one another? How do we split the possible angle divisions among the 3 triangles? So I think there's a lot of interesting, groundbreaking new work with more than 2 colors just in the plane. And then we can take it, to 3 dimensions and higher dimensions afterwards when we understand the basics.
That's a great point. That is a good idea.
You see that sometimes on your video screen, because that's RGB are small dots that are into the screen. So if you look at your computer screen with a microscope, you'll find out that it's made up of those colors. And when a pattern moves across the surface, very often you'll find a color mix. That's what gives it to you. So we're viewing that almost on a daily basis and just don't really realize.
Well, actually, that's true. If somebody has a very shirt with a very fine texture on it, you know,
That's right,
and then they
yes.
move on TV, you see all kind of colors flashing. But it's still just two components. You know, one is the sampling by the video camera and its discrete pixels.
Right.
The other one is the shirt.
Yeah.
I'm saying, what happens if you have three independent sources moving against one another? And I don't know if anybody has really explored that particular field.
There's probably something
Will it
that
be
could be
Play-Doh?
animated in a visual tool, a graphics tool.
Mhm.
Might have some abilities to do
Oh,
this.
absolutely. I would just say take somebody who has, you know, little computer graphics skills, and they could probably set that up within a day. And I'd love to see some experiments done and see what kind of strange effects may appear.
What you start to get, I've done this in the lab a number of times with color and so on. You also have to be very careful in how you interpret some of that material, because very often the brain will take over the thought and give you a false reading. And of course, that's what was happening with that Moire pattern I showed you from a few minutes ago, is that it's not just simply the physical aspect that's going on or the mathematical aspect of it, but it's also the psychological and the physiological aspect of how the brain interprets that happening. And there have been a number of studies at a number of universities in psychology departments where they've studied that. And
Yes,
some of
I
you
guess.
know, I'm trying to think of his name now, at Rhode Island School of Design, that has spent a good deal of time with Professor Brown doing research on that very question.
Yeah, I think we're so conditioned by our, you know, cubist architecture that we have all around us, that we try to interpret whatever we can see as rectangles and right angles. And so sometimes just staring at the Penrose two-dimensional tiling, you know, we see three-dimensional structures that pop up, you know, with cubes pointing in a corner towards us and the like. And so the brain takes over, tries to make sense of what they see in terms of what they expect, and that is cubist architecture. And there are more effects like that, and it's really it's an extra complication.
I want to ask one question, Carlo. I know you just said to move, you know, go into something simpler than 3D, 4D analogs, 2D, 3D, 4D analogs, and just work with the surface. But you were talking about polytopes like this 120 cell. You showed a tesseract, but and then this is a 24 cell. So were you talking about actually every face within and externally and internally can rotate and have the Moire patterns?
Well, I mean, there are many different questions. The simplest question that would come to my mind, you start out with two exactly identical polytopes in this wireframe mode, exactly overlapping. And then you just start along one particular axis, rotate the two against one another. And so some of the edges will split and drift apart, and you may get just interesting pattern just because of two simple wireframe models against one another. And of course, then the question is, okay, but you know, maybe we should not just have two, we should keep the threefold symmetry of something like that's made out of tetrahedron, and so then rotate, you know, three objects in maintaining tetrahedral symmetry or something like that. I think there's an infinite number of really interesting experiments that we can do here.
I think it's, if I understand it right, we're also trying to figure out if we do a projection onto a face, what Moire pattern to put on those faces. And so I think that might be an interesting topic for a deeper dive.
Well, Prithvi's done that by putting different patterns on different faces of his forms and showing what happens when they rotate. Is that what you mean, Al?
Yeah, but he's got the different shapes, the triangles, the squares. My question is there a deeper dive on, is there different shapes to put on those faces based off of what patterns might underlie if it's a deeper structure, that if it's a structure that's made from a closest packing of spheres, or as Bonnie had some of those looked like interfaces from that from those four-dimensional objects, do they project out onto a face? And then if you moire that face with that shape, what happens? I'm not sure I'm articulating myself well. I just thought that figuring out what patterns to put on that face might be a deeper discussion. And also, I mean, if you really zoom in, the one face is a little smaller than the one above it. I mean, if you really start to kind of layer it down, there's a little bit to be said about the angles of both the rotation and then how each point is connected, because it's the inner one's always got to be just a hair smaller, right? And if we have several layers like that, at what point do you have enough layers so that you have just one? Is the inside one just one smaller than the outside one of points around that circle?
Actually, that brings up a question for Prithvi. In your models, you have two plates of acrylic that define the faces, and they have obviously some thickness. But then on one of the surfaces of this acrylic sheet, you actually have your moire pattern. Did you put it on the two sides of the two acrylic sheets that actually touch one another so that there's no offset between the two sheets, or how did you do that?
I tried, I guess, all versions. The thing is, they scratch if you put them on. They was, because of the motion and because they're physical structures, there's dust and stuff as well that comes through. So I put them on the opposite sides, basically. So
Okay,
not.
but you had your camera enough far apart so that the perspective would not distort the pattern, right?
The
Or
thing
the
is, the
acrylic sheets
moment
are
it's,
thin enough.
yeah, the acrylic sheets need to be thin enough for it to close fully. The moment you have any thickness, the box or the tetrahedron won't close fully. So even in these structures, I mean, yeah, the wireframes, like I was trying to make a fully black box, which is why I chose to use alternate checkered patterns rather than the wireframe patterns. Just I wanted to be a black box, and then it expands into this motion in that particular one. But yeah, any thickness in the physical structure doesn't allow full contraction, I guess. Yeah.
Sam, are we sticking to our 12 o'clock deadline, or?
Well, this can continue for as long as all of you would like it to continue.
Okay.
Yeah. I have a short video here that might show you a little bit about what I was saying and asking you about the, if you had a cube, whether it's a fourth dimensional cube or it's a three-dimensional cube, in which it appears only as a single cube, but then undergoes that geometrical transformation for a full cycle of 360 degrees, and you see the cubes that are packed inside of a single cube. So if you'd like to see that, it's about a minute long, I think, or so.
Yes.
Yeah, go ahead, Joe.
Okay, so can I have the screen, I guess, share screen?
Yeah.
You see this yet?
No.
I didn't bring it up on the right one, then I did it. All right, where to go?
Also, the other thing, if I can just add quickly to Carlos' question, is it also matters how much zoomed in the square grid is for the animation to look nice or not, I guess. So if it's just like four squares, that's not going to make a moire pattern look good. 8 or 12 or like many more, then the Moire pattern emerges more. And if you put too many, it becomes too much as well. Yeah.
Yeah, at some point, the resolution of the zoom projection will wipe out things, right?
It's a problem for the videos as well, for like a computer animation of it, I guess. One can't really see it. Yeah.
You see it yet?
Yep,
It's coming.
Here we go. Great. Now, tell us again, what are we looking at? What is it we should
Yeah.
focus on? What exactly is
cross-
going on?
Cross your eyes slightly, it'll become three-dimensional.
I'm on low resolution right now of some sort.
I can see three-dimensional, so do run the movie again and do the trick.
Can't find my start and stop.
Oh, it's in the middle, bottom middle.
This one?
In the
Ah,
middle, in the
here.
middle of the line, down below is a little triangle.
Here?
No,
Oh,
in the middle.
go to the left, Joe. We passed it.
Now to the
Okay.
right. The three images in the middle below the line.
I got a lot too many images below the line, just all my other. Let me see if I can.
Center bottom of the screen,
There it is. Okay.
Joe. Center bottom of the screen.
There it is.
Okay. Oh, that's cool.
Now that's actually a cube, and these are all the planes in passing through the center. That's why it gives you the impression it's an octahedron. But it's actually the faces of the cube, and it's multiple cubes. And if you look at this with left eye, right eye, cross-eyed technique, you'll be able to see it in 3D.
That's what I'm doing, and it's quite successful. So run the movie again.
Bigger. And there all the cubes
Yeah.
expand,
Yeah. Mhm.
and at this point, you basically have the cube octahedron and the tetrahedron. So it's an array of a close packing of the hexoctahedron and the octahedron. So in a sense, there's the thought about if you have these packed with or placed on this system of a series of Moire patterns, what would that combination of those patterns, if they're transparent, have a transparency to them so you can see through the system? What kind of bulk or what kind of patterns would you start to get? Because you should be able to determine, if you knew the equations for it, as to what the angles of rotations at every different level would be because of the combination of the Moires that you get. I mean, that's a common technique that's used in crystallography when you start to look at high-powered images. Very often you can find imperfections in the crystal. You can find the atomic array of the atoms that make up that particular crystal and so on. Those are the patterns that you're looking at in material science and crystallography and so on. And so it's trying to work those out and understand what that transformation is.
So what I'm really seeing is a 3 by 3 by 3 array of the regular Jitterbug models of the cube octahedron, right? That's really what you're displaying here. 3 by 3 array of the
Yes.
Jitterbug model of essentially the cube octahedron.
Yeah.
Looks very good in 3D. And you know, the funny way I hold my hands, that blocks kind of the wrong images. So I can only see the left image with my right eye and the right image with my left eye. I carefully adjust my hands to do that.
Oh, you're
And then-
seeing the back, so if you're doing left and right, I mean, left. Yeah, but if you do a cross-eyed,
Yeah, absolutely. I do a cross-eyed and it's
Yeah.
quite powerful. Super.
That's great.
okay. So again, that brings up that question of how would the Moire pattern start to look like on that system? So anyway, that's
And again, it gets to the deeper question, what exactly is the construct that forms the Moire pattern? If we only have, you know, two stencils, basically, we can do sort of a Boolean union of all the black areas in it. And if they completely fill space, then you get a black box. And if they completely overlap, you get a checkered board box and so on. But as we go to more interesting shapes and we want to do more than just something in 2D, then the question is, you know, what exactly is the underlying atomic level mechanism that forms the Moire pattern? You know? And so I think there is more avenues to be explored in that domain.
I think on that projection that Joe had, when it was transparent, and if you looked through, you were kind of looking at an angle where you almost saw a triangle with a solid line, and then like four triangles on top of it, like as you were looking through it, because it was transparent. So my question is, if you use that as the pattern on that face, and replicated it on a smaller scale, what would that interference pattern look like? Because it's represented on the surface by what you see through it. Is that? I'm definitely having too much coffee today.
Well, we needed the coffee
Probably
because
the
this was a
black
very
box.
powerful presentation, very powerful, intriguing discussion. So more coffee is all we need. You know.
Did you see that on his projection when he had that lock that the transparent? If you looked through it, did anybody else see that shape inside? Could you put it back up for a second?
oh, I
No,
it'll take me a
no,
while.
but no, don't worry about it.
What that is all of the 6 planes of the cube are passing through a common center of the cube. So you're seeing a nolid. You're not seeing, you're seeing a hollow form. I'm not sure whether you're familiar with the nolids or not, but see how the faces go in. The model that was shown early on. Prithvi, you had a model on the table, I think, that was a packing of tetrahedron, but all the faces went into the center of the tetrahedron. No, they didn't. They were the edges. One of the faces was missing. That would be falling in the class of the nolids. And so basically it has no volume if you think about it in a mathematical sense. The only problem is that obviously when you make it, it's got a model because every face has got some thickness. So I like to tell people that mathematics is thought. Mathematics is not reality. It's only thought. Because a point does have dimension in the real world. It's just that all the dimensions are very, very small and very tightly packed and probably start out as a sphere. But every one of your polyhedra could be thought of as a point. Has volume. But anyway, that's the way that we have that configuration of the cube, with all of the 6 faces are really passing through each other, passing through a common center. So then it starts the expansion. It starts the rotation and translational transformation of the in this particular case is the chiral polyhedral form of the jitterbug. I mean, usually when most people think of the jitterbug, they think of it and make models of it. They only use a single plane. They don't show that the plane has two faces and one face rotates clockwise and the other one counterclockwise. So that's what gives the chirality to it. And that's one of the things I think that Prithvi is really interesting about how your moire pattern starts to show that transformation that goes on in those forms. And I think that if one started to look at what would these introduce motion to the fourth dimensional forms, such as the Octahedron or the cube or some of the simpler ones, that you'd start to see some of that really interesting combination of what's going on in that transformation. Because they should be able to transformate in fourth dimensions like you do in a three-dimensional form. But I don't know people or anybody who's tried to study that, because I think that packing and that transformational array, that motion that goes on, start to show up a lot of things that we're not very familiar with. Now, I love your work. I love your work. It's great.
Yes, indeed. Very good. Thank you, Prithvi.
What was that?
Really?
Carl?
Thanks, guys. Show
Great
one
talk.
last tetrahedron.
Thank you much.
Yeah.
Nice.